Hello, everyone. Welcome to the FusionEPtalks, a student-led webinar on fusion science and technology. The masterclass today will be around 40-45 minutes long, and then we will have 10-15 minutes for a question and answer session. My name is Dhaval, and it gives me immense pleasure to introduce our speaker for today, Dr. Dmitri Orlov, who works as a research professor in the Center for Energy Research and Department of Mechanical and Aerospace Engineering at the University of California, San Diego. Dr. Orlov received his BS and MS with honors in applied physics and mathematics from the Moscow Institute of Physics and Technology. He then earned his Ph.D. in 2006 from the University of Notre Dame in Indiana, where he did pioneering research on the aerodynamic plasma actuators for aerodynamic flow control. In his thesis, titled Modeling and Simulation of Single Dielectric Barrier Discharge Plasma Actuators, he developed the first principle-based engineering models for plasma actuators, verified them against experimental measurements, and demonstrated their application for simulations of flow control on the airfoils. After completing his Ph.D., he was at the Department of Physics at the U.S. Air Force Academy in Colorado Springs, where he worked on MHD and PIC modeling of streamers and glow phases of the atmospheric barrier discharges in application to flow control. Dr. Orlov then joined the University of California, San Diego Center for Energy Research in 2008, and he is presently working at the DIII-D National Fusion Facility. His research is focused on the control of the edge instabilities in high confinement regimes in present-day tokamaks, as well as future burning plasma devices, including ITER, on transport in the core and edge of the tokamaks under 3D non-axisymmetric perturbation fields, and also on heat and particle transport to the divertor surfaces. Dr. Orlov is a member at large of the American Physical Society Division of Plasma Physics Executive Committee, a coalition for plasma science vice chair, and also a member of the U.S. Transport Task Force Executive Committee, as well as the lead organizer of the Frontier Plasma Science Collaborative Research Facilities Joint Call for Runtime Proposals from 2021 till today. Today's masterclass topic is quite unique. It's the first time that we will be talking about a crossover of space exploration and fusion research. The development of material that can withstand extreme heat flux environment is very, very crucial for both the successful exploration of the solar system as well as the realization of fusion energy. To this end, a study of carbon ablation is in high heat plasma relevant to hypervelocity spacecraft entries was conducted in D3 tokamak as part of the Frontiers in Plasma Science campaign. Spacecraft heat shields that can withstand high heat flux are required for exploration missions to the gaseous giants and for hyperbolic reentries into the Earth's atmosphere. However, testing and modeling material performance in this regime is challenging due to the lack of adequate ground testing facilities. Dmitri will be talking about how fusion research can benefit our design of future spacecraft heat shields and even more exotic applications. So without further delay and spoilers, I'll now mute myself and hand over to Professor Orlov. Welcome, everyone, and enjoy the talk.
Hello, and thank you for the introduction, and thank you for inviting me to speak here today. Let me share my screen. Perfect. So thank you for such a nice introduction. And today's talk is on the crossover of space exploration and fusion research. And as you could hear, as Dhaval was saying, this is probably going back to my past as an aerospace engineer and my present as a nuclear fusion scientist, trying to find the common things between the two. And this talk will be about the work we did on the D3D tokamak with a lot of contributors helping here that I list on this slide. People are from the universities in the US, in Europe, from national laboratories. There are students, graduate students, undergraduate students on the team. And of course, there is the whole D3D team that was helping us to do these experiments. As you've heard from this short abstract earlier, there is a common interest in spacecraft research and in fusion, because both crucially depend on the materials. We need to develop the materials that can withstand extreme heat flux environments for both of these research topics. And I will focus in this talk more on spacecraft heat shields because those are needed for the exploration missions to the gaseous giants that we've done in the past and will do in the future, or for hyperbolic reentries into the Earth's atmosphere. It is extremely difficult to test the materials under those conditions on Earth. So we have to come up with the models and hope that the models will behave as we predicted when we go to other planets. The problem here is the lack of adequate ground testing facilities on Earth. And when we were coming up with the ideas for these experiments, we just thought of the tokamaks and decided that tokamaks may be a good test bed facility to study high heat flux regimes for different materials. So I will show you how the D3D L mode edge plasmas can reproduce the flow velocities, the high heat flux that were experienced by the Galileo's probe when it entered the Jupiter's atmosphere. The outline of my talk is like this. I'll talk about the thermal protection systems first, then we'll talk a little bit about the D3D tokamak, and then I will talk about two types of experiments that we've done with the stationary carbon ablation rods and then with the pellets that we launched into the plasmas. So let me start with the thermal protection systems. The atmospheric entries usually qualified as an extreme environment, and NASA used the probes successfully in different regimes. Some of those regimes were mild on the peak heat fluxes, like the Mars Viking here. Some of them were extreme on the peak heat fluxes, like Galileo or Pioneer Venus. And what I want to show on this figure on the left is, if you think about the peak heat fluxes, the D3D tokamak can give us heat fluxes that are comparable to the most extreme ones that the probes and spacecraft experienced when entering Venus or Jupiter. And when NASA sends those spacecraft to other planets, it usually wants them to enter more or less untouched. So it uses heat shields, it uses ablative materials, and the ablative materials have been used successfully by NASA for the last 60 years. And I think it will be used the same way in the foreseeable future. A little side note here, when I'm talking about ablation in this talk, by ablation, I mean removal or destruction of something from an object by either vaporization, and this process is called sublimation, when something goes from solid state into gas directly, by chipping, or spallation, when things just chip off and fly as large pieces into space, by erosive processes, or by any other means. This is all ablation. The objective for the thermal protection system, the minimum objective with a reliable performance, is the material failure modes need to be well understood. And when we choose the thermal protection system materials, usually we choose between the low density materials, which are typically better insulators, or the high density materials, which I say typically better ablators. Because ablation is a good process. Ablation usually absorbs the energy, but too much ablation may not be good because it may lead to shape changes, as you will see in some future slides. And these shape changes can change the aerodynamic behavior of the spacecraft that are in the atmospheres. But ablation is probably the best process that we have to remove the heat now when the spacecraft enter other planets' atmospheres. So here I'm focusing on one particular spacecraft, and this one is the Galileo's probe, which was sent to Jupiter many, many years ago. The probe entered Jupiter's atmosphere around 1995, and on December 7th, 1995, it entered the Jupiter's atmosphere at a relative velocity of almost 50 kilometers a second, 47.4 to be exact. The temperatures at the shock layer were approximately 16,000 kelvins. And if you see this image on the left, this is the Galileo's probe, and this is the thermal protection shield. With this tip at the bottom is the front, where it was entering the Jupiter's atmosphere going down. All the instrumentation in the probe was hidden behind this thermal shield. The image here shows the shape of the thermal shield, with the nose being here on the left and the back sides covering the instrumentation. The shield was about 152 kilograms, and the total mass of the probe initially was 335. So that was a lot of the total mass that was sent to Jupiter. When the probe went into the atmosphere, what's shown here in yellow is what was ablating. So it was ablating everywhere, and on the nose and on the sides. And at the end of the mission, the thickness of the front was about 10 centimeters, down from 14.6, but the sides ablated so strongly that there was only 1 centimeter of material left. This was not something that the NASA experts expected. It was way too much loss of the material, and we were lucky that we put a bit more material with some safety margins so that 1 centimeter was still there. The mass went down to 70 kilos. The shield lost, the heat shield lost about 79 kilograms of ablation, and that happened over 70 seconds of the entry. So that was such an extreme heat flux that peaked at about 15,000 watts per square centimeter. How do we know that information? There were some ablation sensors impregnated into the heat shield. There were about 10 sensors which were recording the ablation history and sending the data back onto the orbiter going around the Jupiter and back to Earth. That's how we know the ablation history at different parts of the heat shield. Those were called ARAD sensors. Before the spacecraft was even constructed, before it was built, there was a bunch of tests done with laser irradiation, with the ballistic range, with the plasma arc jet experiments. But when we got the data from those sensors back on Earth, and this is shown in black dots here on the left figure, and when we compared that to the simulations, it appeared that the recession of the thermal heat shield material at the nose here was overestimated, and the loss of the material at the back was severely underestimated. This is from Moss and Simmons, 1982 paper. So the conclusion was that we need some better models to explain the behavior of the carbon ablators at the extreme heat fluxes. And it was also clear that no single test on Earth could reproduce all features of material ablation, like high heat flux, boundary layer, heating history, spallation, and all that. And this is where we came with the idea that modern tokamaks can help solve some of those questions, because we probably can reproduce the conditions a little better than other types of tests. And this is where we come to the D3D tokamak. And since you're all from Fusion, you probably know what D3D is. It is a tokamak, Department of Energy National Fusion Facility. It is located in San Diego. It is serviced by the General Atomics Company for the Department of Energy. D3D is a medium-sized tokamak with the major radius of 1.67 meters. The minor radius is about 67 centimeters. We can do 5 to 7 second long discharges. The walls in the machine are all carbon walls. So if we want to study the carbon ablation, this is probably a perfect environment to do those studies. And D3D has the Frontier Plasma Science experiments campaign for Frontier Plasma Science. The experiments are allocated about 1 run week a year. This can fit between 4 to 8 experiments, half a day to a full day. We usually have a call for proposals for these experiments, which comes out about APS DPP meeting in the fall. There is a website with all the information. The call is open to all participants, US and international. The topics for these frontier plasma science experiments are usually not nuclear fusion, but some other plasma physics that can be done in the tokamak environment. And the runtime is usually funded by the Department of Energy, the Fusion Energy Science Office. So for our experiments, we have focused our attention on the floor of the tokamak. If you can see here on the floor, on the shelf, there is that little black dot, which we call the DIIMS system. DIIMS stands for Divertor Material Evaluation System. It is a nice way to introduce different material samples in the lower divertor to hot tokamak plasmas. We usually place an ablator and it's flush with the surface for the PMI experiments. And we have a nice view of this DIIMS port, and we can change the materials that we expose literally between the shots. We need about maybe 15-20 minutes to lower the DIIMS, the DIIMS head, replace it with something else, put it up, pump it down, and run the next shot. As I said, this DIIMS port is a well-documented location, maybe one of the best locations with the diagnostics on all the tokamaks. Please forgive me if you're a fan of another tokamak. I like DIII-D, and I think this is a great spot to study different physics. Here is the top view of the DIII-D tokamak. The DIIMS port is shown here as orange dot. For these experiments, we have the reciprocating X-point LANGMA probe at the same radial location. We have the IR camera looking in this particular experiment sideways, but with the view of the DIIMS port. We have the visible imaging, which is looking at this rectangular region right from above. So this is a vertical view. We have the multi-chord divertor spectrometer located right at DIIMS. We have the fixed floor LANGMA probes next to it. We have the tangential TV with different filters that we can use. We also have the divertor Thomson scattering system in that region. We have the wide spectral emission spectroscopy. This is all the information that we need for analyzing the results of our experiments. We also have the core plasma measurements as we use them for any other experiments on the DIII-D, and we get the electron and ion densities and temperatures from core Thomson scattering, from CER spectroscopy, from ECE radiometer. We have filterscopes, visible Bremsstrahl and bolometers that we need to analyze the results of these experiments. So we thought that we can use the DIII-D tokamaks because the conditions in the plasma edge are somewhat similar, not exactly, but close to the ones that the Galileo's descent probe experienced when it went into Jupiter. The gas composition, of course, on Jupiter is hydrogen and helium. We have deuterium. In the ideal situation, we can actually use hydrogen and helium as well, but these experiments were done in deuterium. I want to make that clear. The temperatures are about 100 eV in the Galileo Jupiter's entry, and they're about 10 to 200 eV in the edge of the plasma in DIII-D. The typical densities on Jupiter are 10 to the 9th meter cubed, 1/meter cubed. That's a lot lower than the DIII-D densities, but you should remember that the density is a lot higher in front of the descending probe. And we've seen the simulation results for the Galileo's entry, where the density of the plasma in front of the probe was almost getting close to the numbers that we have in the DIII-D tokamak. The velocities, as I said, were about 50 kilometers a second when the probe entered Jupiter, and they're about 10 to 80 kilometers a second, the ion flow velocities in the DIII-D edge. and the heat flux are the heat flux values are very comparable, 100 to 500 megawatts per meter squared in Jupiter's entry, and 50 to 200 that we can probably get in the DIII-D tokamak. So we decided that we will use the material evaluation system DIMES to study the material ablation, and we will modify it a little bit, and I will show in the next slides how we would do that. We were thinking about two types of experiments: launching the little projectiles into the plasma edge, or exposing carbon samples to high heat fluxes. And what we wanted to do is we wanted to take those semi-empirical models, the models that were created after the Jupiter's mission, the Galileo's mission into Jupiter. And we wanted to test those models and see whether they stand, whether they are confirming our observations in the regimes close to the Galileo probe's entry. And we also have some codes that model the dust transport in the tokamaks, like dust T code. So we wanted to compare the predictions from those codes to what we see in the tokamak when we launch the little pellets. I mentioned these semi-empirical engineering models for carbon ablation, and typically, if you want to get the mass loss rate, you need to know the heat fluxes, and you need to know the heat of ablation coefficients. We can measure those Qs from the experiments, but how do we get the heat of ablation? And that's where the semi-empirical models will come in, because once we know this value, we can calculate the mass loss rate, and from mass loss rate, we can calculate the recession rates on the surface of our stationary rods or little pellets. So there were two major models, at least, that were created after Galileo's probe. One was done by Matsuyama in 2005, and he was saying that we can calculate the heat of ablation through the pressure at the projectile's surface. And the other model was created by Chul Park in 2009, where he was suggesting that the heat of ablation coefficient can be proportional to the projectile's surface temperature. So those would be the two models that we will be testing in these experiments. And using these two models, we can do some simple predict first simulations and just estimate how much mass would we be losing in the divertor region of the DIII-D tokamak based on some model discharge that we had before the experiments. That modeling suggested that we actually, in the L mode conditions, should see ablation of millimeter-sized carbon pellets in the edge plasmas. That's good. So we decided that we would do these two approaches, and the approach one would be using the DIMES system, but modifying it to hold different carbon ablation rods. These rods are about maybe 2 centimeters tall. And the other modification would be to do a different DIMES head that would hold a launcher system, the launcher system that would launch little carbon pellets, shoot them into the plasmas. So let me talk about the first approach first, the stationary carbon ablation rods. As I said, we reconfigured the DIMES port, and we reconfigured it to host 3 rods, 1.5 centimeter above the DIMES head surface, about the floor surface. And for this experiment, we were playing with different shapes. So we decided that we want to look at 3 shapes of the little cylinders. As you can see here, the middle one is perfectly round cylinder. The other one is a wedge cylinder, so we made it look similar to the Galileo probe, and the flow would be coming from this wedge side. And the third one, we decided to do a cylinder with a little cavity that we cut in that cylinder. The thinking behind that was that this cavity may actually be somewhat useful. It may be trapping the neutral particles, and it may have a little detachment region there. And maybe the detachment region would be shielding the carbon rod from the plasma heat fluxes like we usually do for the plasma detachments in the divertor regions of the tokamaks. And maybe by having this little cushion of neutral gas, we can lower the heat fluxes coming to the rods. So we designed this, we built this head, and we located it next to the outer strike point in the D3 tokamak, usually when we have the highest heat fluxes. We also had a few rods with 30 micrometers silicon carbide coating. If somebody's interested in those results, I can probably also show them. I have them in the backup slides. So we stuck those rods into the D3D tokamak and measured what kind of heat fluxes do we get in the region near the carbon rods. The plunging X-point length probe that was located at the same radius went up and down into the edge of the plasma, and on a series of the discharges where we exposed the carbon rods, we had the heat fluxes measured by that plunging probe on the order of 35 to 45, around 40 megawatts per meter squared. And the y-axis here is the height over the surface. So this is going up. The relative size of the carbon rod, about 1.5 centimeters, is given here on the left. We also were measuring the heat fluxes on the surface using the floor length probes. These are fixed length probes. They are over the surface here, and if we do some plasma sweeps back and forth before the exposure, we can collect the information and come up with the profiles, construct the profiles. The red profile is the smooth feed into the length probe data for the heat fluxes. Heat fluxes are given here on the y-axis, and the distance from the strike point is given here on the x-axis in meters. Excuse me. The black one is the typical ITER fit that you're probably familiar with. So both of these plots agree that the carbon rods experienced about 40 megawatts per meter squared heat fluxes where they were in the plasma, in the edge of the plasma region. When we exposed them, this is probably one of the best examples. The strike point was located here next to this number 3. So this rod that ablated the most, and you can actually see that ablated region, it was closest to the hottest region, to the highest heat fluxes. And we can see, we could see a lot of ablation in the multi-chord divertor spectrometer, MDS. This is the chord 5 in this case that was looking directly at the dive port, and you could see that there is a lot of emission in this wavelength range between 510 and 517 nanometers during the whole time of the exposure of those rods to the high heat fluxes. And when we measured those rods after the experiment, we actually did the measurement before the experiment and after the experiment. Some of the rods lost up to 120 milligrams of ATJ carbon material. How do we know that it was ablating? We were also looking at the SWAN bands in this case. SWAN bands is the molecular C2 emission lines. This was seen in the WISE diagnostic as well. And we could see that the SWAN bands, they usually indicate that there is fast sublimation happening. And sublimation, it is the transition from solid state to gas state without any going through liquid. It's directly from solid to state. These very bright SWAN bands. I had Adam McLean, who is an expert on the SWAN bands, running to us after the experiment saying he's never seen SWAN bands as clear as on these discharges. So this was definitely suggesting that the process happening on those rods exposed to the plasma was fast sublimation. And this, just to relate you to the aerospace results, this is very similar to what is often seen in plasma wind tunnels when they investigate the ablators. These are the swan bands from one of the aerospace works on the ablation of the materials. Same molecular C2 emission lines that they see. Good. That's a good result for us. This slide here, I'm showing you how we were observing the sorry, I need to move this a little bit. The bar blocks some part of my screen. So here we were looking at those rods exposed to the high heat fluxes during the plasma discharges. So this is one of the discharges, and the picture on the left is what we could see with the fast visible imaging camera looking vertically at dimes. The dimes port is located here. This is a zoomed view with the 3 rods that you can see here. One of them is getting the highest heat flux and shows up as the brightest white spot on the visible imaging. This is that rod that I was showing earlier, the one that ablated the most. And what we can do is we can convert the emission, the visible light emission from those rods, which is given here as function of time, into surface temperature. If we assume some parallel Qs of 30, 34 in this case, and we can estimate what the surface temperature was based on the visible imaging light that we're getting from those rods in the experiment. We could also take those rods out after the experiment, of course, and analyze them in the post-mortem analysis. And for that, we've used the optical 3D surface profiler to measure the exact surface recession. And this figure in the middle shows in the red line the original round shape of the rod that we stuck into the plasma before the experiments. And next set of lines, the brown to black, is showing the measurements of the rod by the optical 3D surface profiler, and we can see how much material eroded as function of distance, and we could calculate the erosion in grams per centimeter squared per second for 3 different rod types. The concave rod was given here in blue, the round rod in green, and the wedged rod is the red curve. That's the highest ablating case, and we could calculate that to be about 1×10⁻² grams per centimeter square per second. So these were our experimentally measured ablation rod rates in this case. Now, what I was showing you before were the 2 models by Matsuyama and by Chul Park. And since we know our conditions, we know the wall temperature in this case, about 37,4100 Kelvin. We know the heat fluxes of 30-40 megawatts per meter squared. We can plug those numbers into Matsuyama's model in this case and get what he was predicting in his model. And that would be 4.2 to 9.1 10⁻² grams per centimeter squared. If you look at these numbers that Matsuyama's model was predicting, and these numbers that we measured experimentally, his numbers are definitely overestimating what we had. They're a bit close to the wedge case, but still somewhat above it. Now, the other model that I mentioned was the Chul Park's model, and he uses if we use the same wall temperature and plug the numbers into his model, we get the mass loss rate of about 0.8 to 1.1 grams per centimeter squared per second. And these numbers, if you compare them to the experimentally measured, are actually very close to what we had on the concave and round cylinders. We're basically matching the numbers in the Chilpark's model with what we've measured. Interesting. So from here, we decided to go to the second part of the experiments that we planned, and those were the carbon pellet launcher experiments. As I mentioned before, we had to do some modifications to the DIIM's head. So this is a cross-section of the DIIM's head. We built it with the spring-launched pistons so that we can put some pellet on top of the piston. In the experiment, in the plasma control system, we can send some high current through this vertical wire that holds the compressed spring, and the wire will burn and the spring will be released and the piston will go up and shoot the pellet up into the plasma. This is what we could see. Something's not playing here, right? Oh yeah, now you can probably see the pellet going up. This is us playing in the lab before the experiments, verifying that the pellet goes up and measuring the velocity of about 10 meters a second. And that's about the size of the sample carbon pellet. This is what the manufactured launcher head looks from the top. We had 4 pistons with 4 springs. So we could actually launch 4 different pellets, or maybe even multiple pellets from the same piston. You can see those pellets sitting there on top of the pistons before the experiment. And this is where it goes into the DIII-D tokamak, into the DIIM's port. And we expected the pellet to go up vertically and maybe ablate in this hot region next to the outer strike point. Or if it didn't ablate and if it was sent up vertically faster, it could actually go all the way into the core and ablate in the most hot regions of the plasma in the core. We launched different pellets into the tokamak, and we had 2 different types of carbon pellets. One we call tidal. These are porous carbon pellets, something that you would use in the filtration systems in your home aquariums. And we had the dense glassy carbon. The scale here, you can see how much smaller one is with respect to the other one. And we tried different plasma heating levels of 1 megawatt of NBI power, 2.5 megawatts of NBI power, just to get different heat fluxes. And we launched the pellets at different speeds. Either we compress the spring fully, and that gives us a full speed of about 10 meters per second, or we don't compress the spring fully, and therefore we get reduced speeds, and we could get speeds of 3 to 8 meters per second vertically. Now, this is what we could see in the machine when we launched those carbon pellets. The left movie here is what we could see on the visible imaging camera in the visible light, and you could see that pellet going up from the DIIM's port. This is a top view. This is the view from above, vertically down, and you could see the pellet not just going up, but also going sideways, taken away by the plasma flow to the right side of the image. And you can actually see that when it gets to some hot regions of the plasma, it splits into 2 smaller pellets. Right here, you can see it goes boom to 2 pieces. Now, the image on the right is the side view from the infrared camera, and it doesn't have that nice spatial or temporal resolution, so there are just a few frames here, but you can see the pellet going up and into the plasma. This is the same discharge, same pellet, but looking from the top and looking from the side. From the IR camera, looking at the pellets and analyzing the emission, we can actually get the temperature on the pellet. And this figure on the left shows the temperature in Celsius as function of the height. above the DIII surface. So the DIII is at minus 125 centimeters, and the pellet is going up, and the heats up and the temperature increases. And if we do some simplified assumptions, we can actually extract the heat flux that the pellet receives from this IR image. Of course, this is preliminary result. It needs more thinking, better analysis to get better estimates of the heat fluxes. But this is what we get to extract from the IR camera data for the pellets flying into the plasma. It's interesting, if you saw the images before, you could probably see that at some point the pellets become mushroom shaped like. So there is this front ablation cloud, there is a little tail behind, and you can see the same shape in both the visible image and from the fast cam and in the IR camera image on the right in the infrared. This is the side view, tangential view. Now, what we could do with this information, we could actually do a three-dimensional reconstruction of the pellet trajectory, because as you could see on these images, we can look at the pellets from the top, we can look at the pellets from the side. That's probably enough to try to reconstruct the 3D path of the pellet in the DIII-D discharge, and we can try to compare the path of the pellet in this case to what we have in the UH-DUST simulations. And UH-DUST is a particle transport simulations code. And originally, when we ran the DUST simulations, they gave us this black line saying that the pellet was expected to go up into the plasma and then be swiped aside without even reaching the separatrix and going into the wall. And this is a 3D picture on the top right with that black line showing the trajectory of the pellet. Interestingly, this was not anything that we've seen in the experiment where the pellet was in fact sucked into the plasma. And that made us thinking of what's missing in the models. And we decided that one of the things we should do is probably think about the J cross B force on the pellet, because it's now not a tiny dust pellet. It is a millimeter-sized pellet, and there may be a J cross B force acting on the pellet. So inclusion of that force in the model now gave us the red line, which was going now vertically into the plasma. And camera is much better. So that was good. We were able to improve on the simulation models in this case. What we could also do was try to estimate how much material was ablating from those pellets as they went into the plasma. On DIII-D, we have the electron density measured very fast by the CO2 laser interferometer. Of course, we have a lot of diagnostics like Thomson scattering or what's the other one? I'm guessing Thomson scattering is probably the better one, but it doesn't have good temporal resolution for the time that pellet goes into the plasma and ablates. We had to rely on something that's really fast, which is the CO2 laser interferometer. It gives us measurements along 4 chords, 1 mid-plane chord, 3 vertical chords. So I worked with Mike Van Zeeland to inverse the data and try to get an estimate of how many electrons were in the plasma as function of radius. So this plot on the bottom shows the electron density as function of time and function of radius in one of the discharges where 2 pellets went into the plasma. You can see the density going up here. And we could convert that into the number of electrons, and assuming that these electrons come from the fully ablated carbon, we could actually estimate how much carbon was deposited. And at the peak, that gave us the number of about 0.2 grams per second of carbon deposited into the core of the DIII-D plasma. UH-DUST simulation can also calculate those things, but when we ran the code initially without any shielding, any ablation shielding, the numbers were so much overestimating what we had in the experiment you can see that for two sides of the pellets, we were getting a lot more ablation, and we had to implement some ad hoc shielding model. And then we got the lines that are here, the solid lines, the solid red and solid blue for two sizes of pellets of 3 and 3.6 millimeters. And those numbers were now giving us something of 0.2 grams per second, quite comparable to what we had in the experiments. Nice, good result. Now, when we were sending the pellets into the plasma, we've noticed something strange happening. And here I want to mention, as I said before, what we can get in the thermal protection system materials is spallation. And this is not when the material ablates nicely. This is when you get some chipping of the material, when it chirps and when it is destroyed. This is not optimal behavior, and usually there is a threshold in heat fluxes for the materials when they start exhibiting the spallation. And this is not the way that the material should behave. We should probably try to stay away or delay this zone by as much as possible, because that would typically lead to very different aerodynamic characteristics that would lead to loss of the ablative material that won't be used for ablative heat flux reduction. Usually this spallation process has some kind of a threshold after which it kicks in, but it was estimated that when the Galileo's probe went into Jupiter, the spallation accounted for about 10% of the mass loss, and this is the mass that needs to be sent into space that we're paying for, and that's lost through spallation. Interestingly, that when we were launching the glassy carbon spheres, we saw a lot of different sparks, shards flying around, and this is the indication of the spallation process that was happening on the surface of those glassy carbon spheres. Once that spallation removed a bunch of glassy material from the surface of the pellets, then you could see the nice little spheres flying further into the plasma, and the normal ablation process happening from there. Here are a few images from a few discharges with those glassy carbon spheres, and you could see a lot of spallation, a lot of shards flying around, similar to what was observed in the materials that were tested for the Galileo's descent probe. As we were also looking at the meteoroid physics, we had a planetary geologist, Chris Mehta, a recent PhD, working with us, and he was looking into the problem of meteoroid ablation in different planets. Actually, his original topic was looking at the delivery of the organic material by meteoroids and how that could have survived the ablation during the atmospheric entry, and how that could be delivered to Earth safely in the past, if that was the way that the material was delivered from space, the organic material. So he was looking at the models, and he was using the Bland and Artemiev 2006 model. Those people came up with the model for the velocities of the meteoroids and the mass loss rates of the meteoroids as they enter planetary atmospheres. So Chris did a few numerical tests using different heat of ablation values in these models, and he was using different heat transfer coefficients for radiative heating, for convective heating, to study the ablation of a carbon material meteoroid entering the atmosphere, and with a density of 14.8 kilograms per meter cubed. He was using the Q values from the models that I've mentioned before, Park's and Matsuyama's models. He took the initial mass of the meteoroid of about 339 kilograms, used the drag coefficient of 2.2 that goes into the equation of motion, and he assumed the initial objects to be conical in shape, similar to maybe the Galileo probe in this case, because he wanted to make the parallels between the Galileo probe and our studies in the D-III tokamak and the meteoroid ablation in the atmospheres. And he was calculating the mass loss rate as function of height. You can see with different CH and Qs, different models start from the same mass and different height, but end up with different masses on the Earth surface. He was looking at the velocity as function of height, the mass loss with respect to time, and the mass loss with respect to altitude for different Q values in this case. And he was saying that the models seem to be given reasonable data for the Jovian atmosphere entries. And the best result he got was with the Q value of 81 megajoules per kilogram for the Q, and the heat transfer coefficient of 0.1. This was probably matching the Galileo's atmospheric probe entry data the best. And he was also saying that the radiative heating results were producing more mass loss compared to convective heating. So this was us trying to use the data from the D-III-D tokamak that we've got into those experiments, the understanding of how the carbon ablates on the high heat fluxes, to understand the ablation of the materials in the meteoroid entries into planets. So the conclusions for this talk would be that for the first time, we've used the D-III-D tokamaks successfully to use the carbon ablation in high heat flux regimes relevant to planetary atmospheric entries. We've taken two engineering models by Park and Matsuyama that were created after the Galileo's entry into Jupiter to explain why the initial results didn't match the measurements. And we've tested these two models, and we found that Park's model predicts mass loss rates nicely for the concave and for the round rods. And we've noticed that Matsuyama's model over predicts the loss rates, but is more close to the wedge-shaped rods in our experiments. We also observed both the fast sublimation and the spallation in those experiments, and we compared the results to our dust transport simulations. And we tried to expand our results and our models to understanding the meteoroid ablation. And they seem to be given results. The models for the meteoroid ablation seem to give results reasonable for the meteoroids and for the D-III-D tokamak data for Jupiter. So with this, I will stop. I probably talked for way too long, 45 to 50 minutes, but I hope you didn't get bored. So if you have any questions, please go ahead and ask. Daval, you can manage the question section.
Thank you so very much, Dmitri, for the wonderful and insightful talk. It is really something that I have heard for the first time, and I'm pretty sure we already have some questions from the audience.
Thank you, Dr. Orlov, very much for the talk. It was very interesting and very out of the box with what we are used to, at least in fusion topics. I wanted to ask you, because you mentioned about a plasma wind tunnel earlier in your talk. So I was a bit curious. You could give some details about how a plasma wind tunnel is different than the kind of plasma that we can get at tokamak, because I can guess there is a difference in density and the heat flux that are achievable. And I don't know if you already talked about that. Maybe I missed it in.
Yeah, I'm guessing you're referring to this slide.
Yes,
and,
exactly.
I have a reference here. I was not involved in that work. This was something that was brought to my attention by one of the DLR colleagues, the German Space Agency colleagues. I can probably send you the reference, and I don't think I can talk about this. This is something not my expertise at all.
Okay, thank you very much. And I had also a follow-up question in my message earlier that was if you could comment about if you need to account for a difference in the time scale of the transient between, for example, a Helm pulse and the typical time scale for re-entry in an atmosphere, because at the beginning of your talk you said, okay, the re-entry in the Jovian atmosphere was like 70 seconds. And of course, Helm transient is much. I don't know if there are any difference that you need to account for that.
Where was it? Yeah, I was saying that the re-entry was about 70 seconds. Our exposures were for 2 discharges of about 4 or 5 seconds each. So I think we collected about 9 seconds of high heat flux exposure of our samples. This is in the same ballpark, not exactly 70 seconds, but we could get the high heat flux on the target for 9 to 10 seconds, which is a lot under those conditions compared to any other experiments on Earth. The elms that you mentioned, we deliberately did not want to have any elms. That will, of course, give us a lot more heat flux, but this will be compared to maybe a lightning flash hitting the Meteoroid or lightning flash hitting the re-entry vehicle. This is not the desired regime. That's why we decided to run the L mode discharges without any elms.
Okay, clear. Thank you very much.
We also had a question from Iole. I unmuted you.
Okay, I'm Yole Palermo from CMAT, Spain. Yes, more than a question, it is just a curiosity if there is any group in San Diego also interested in the possibility to use these materials as radiation shielding in future crewed missions, so against secondary neutrons or galactic cosmic radiation. And also, I was wondering which is the role of silicon carbide in this coating, just a coating for these rods?
Yep. So for the radiation shielding, I am not aware, but I need to ask what's going to be used for that. This is an interesting topic. I'll need to look into what materials will be used for radiation shielding. Let me get to the slide. The second question is something I can address. On some of those rods that we exposed to the high heat flux, we had the silicon carbide coating, about 30 micrometers. But what we learned after the experiments was that coating, the way we've done it, did not work nicely for our experiments, just because different thermal expansion rates of different materials, when you apply the coating the way we did it, caused thermal stresses, and those resulted in a very extremely quick peeling off the coating material. So any silicon carbide that we had on the surface of the rods, as you can see here on this plot on several discharges, it just peeled off and went into the plasma. This is the silicon 12 line for 99 nanometers from the spread diagnostic, and as it went into the plasma, there was no silicon on the next shots. We just basically lost it right away. The question is, what will happen if we make a monolith, a whole silicon carbide thing? This is a different kind of question. We did not do these experiments. This would be interesting to see what happens.
Okay, thank you very much. A very interesting talk.
Yes, and I also must mention that since we're doing the experiments in the tokamaks, it's not that we can stick in any material and as much as we want. There is the vacuum committee, which we have to go to and get the approval for any amount of the material that we want to deposit into the tokamak and make sure that it does not go over the allowed limits. Before the experiments, we were told that we're allowed to lose one of the rods, but as soon as we lose that one rod, the experiments are over. We were lucky to have all the rods in place by the end of the day.
I see one more question from Andrei. Please go on.
Yeah, thank you very much for the interesting talk. So actually, I have two short questions. So, and one of them is just a continuation of what you just explained before about the roads with coating. So I probably missed what was the exact reason why you used the coating. And the second small question is why it's silicon carbide.
Silicon carbide is one of the promising materials that get a lot of attention recently, a lot of research, and this is considered as one of the possible plasma-facing materials for the future tokamaks, and there's a lot of research going on that here at DIII-D. So we decided, why not look at if that's the best material. If it's better than just carbon, we should try and see how it behaves. So this was more of a curiosity on our end.
Okay, thank you very much. The second question was related, so you mentioned in slide number 16, so that you had deuterium plasma, like mostly deuterium plasma. And what was the reason? Because was it a deuterium campaign or?
It was a deuterium campaign, so we decided not to push it to the limits. Running hydrogen is possible, but challenging. Can repeat the experiments in hydrogen if we get the time. There will be a hydrogen campaign here for 2 weeks in June, but I don't think we get the time to do the experiments there.
Do you expect a different results, or in the same range of?
It will be in the same ballpark, same range. So I don't expect anything drastically different. Even the upcoming experiments on the origins of life, which are the follow-up on these experiments that we will be doing this week, actually on Friday, we will be doing in deuterium, trying to simulate the oxygen-poor Earth's atmosphere in the early stages of Earth existence.
Well, cool. Thank you very much, and good luck with your upcoming experiments.
Thank you.
Now that I hear about your plans, we definitely should invite you again to hear about the results.
Sure, but that will be a shorter talk probably, because I already talked a lot about all the setup for the experiments. In the new ones, we will be trying to generate organic material in the tokamak.
That sounds really exciting. I don't see any other raised hands or questions in the chat.
Thank you very much. And from my side, I want to again bring the attention to the frontier plasma science experiments that we do here on DIII-D. It's open to anybody from the US or international community. So if you have ideas for any not nuclear fusion experiment that you want to run on DIII-D, whether it's plasma material interaction like I've shown here, or whether it has to do something with the Whistler waves or runaway electrons, please send your proposals. They will be evaluated, and you may end up running really cool experiments on the tokamaks. Thank you very much for having me here.